Okay, welcome to the final lecture of new material. Okay, the final lecture of new material for this course, you'll be glad to hear. On Thursday, I will be going through exam-type questions. Okay, on Thursday. I've already put these questions up on Blackboard. You will get the most out of your lecture on Thursday if you try these questions beforehand. It'll probably take you about an hour, but try these questions before Thursday, and then I will go through them, okay? So they are already online for you. This morning, we're doing a topic that's very close to my heart, which is open channel flow. So in the previous lecture, we looked at some important differences between ideal flow and real flow. And we looked at how to take these into account. In particular, we looked through flow through an orifice, and we met this vena contractor idea and the friction losses. We were introduced to discharge coefficients, which help us take into account that sort of thing. And then we also considered the major and the minor losses due to friction and due to changes of geometry. And this is how we take that into account. And as always, I left you with one final question. Up until this point in the course, we have been considering both internal flows and external flows. And when we looked at internal flows, specifically we looked at fully developed flow, where you get this parabolic velocity profile because the flow is being decelerated and slowed down right at the boundary here to zero. My question to you was, what happens, in fact, maybe if that pipe is actually partially full? Okay, so here, this is where the surface of the fluid is inside there. Or what if there's no boundary at all? Okay, what happens to that velocity profile? So that was my question to you to think about. So let's just think about it. In the fully developed flow, I can hear someone talking if you can be quiet. Hello, good morning. Thank you. So in a fully developed flow, the velocity goes to zero here because of wall friction at the boundary. When there is no boundary to slow the fluid down there, we get a velocity profile like this. So here it's still going to zero because of friction at the boundary. But once we're outside of that boundary layer region, here we have just effectively uniform flow. And so the velocity at the surface is quite fast. So that's why when you're looking at a river, you're looking at a stream, you can actually basically see the velocity of the flow. We have the same situation for flow in a partially full pipe. So this brings me very nicely onto today's lecture, which is where we are going to consider flow in open channels. This is without a top boundary. And we're going to compare those with what we looked at last week. We're going to meet a new number today. It's called the Froude number. Okay, it's a dimensionless number that we use to characterize those flows. And then we're going to understand total and specific energy. Specific energy is specific to open channel flow. Then we're going to do something really exciting, which is look at the hydraulic jump. So what is an open channel flow, or flow with a free surface? In these two images, you can see two very clear examples. This is quite a violent flow on the left. Okay, this is basically after some kind of hydraulic structure which is retaining the flow, and then it's coming out. It's very bubbly. You see it's white, it's not blue, it's not clear, it's bubbly. And then this is a stylized image, okay, of what happens when you've got fluid flowing down an open channel where it's got quite an unusual cross-section. The main characteristics of this flow are, one, that it has this surface, that it does not touch a boundary. Okay, does not touch a top boundary. That means that the pressure here at the surface here is atmospheric. So we have atmospheric pressure here. And the flow is primarily driven by gravity. and this is a key point. So gravity, which is basically creating the pressure gradients, is driving the flow. There are many, many applications of this, including pipelines, fuel tanks, reservoirs, etc., you name it. So Formula One cars, like the race yesterday, okay, they will be considering this open flow inside the fuel tank. So what are the type of channels that we can look at here? We've got circular ones, we've got square ones, we've got an open duct. So this is an open duct. It would be rectangular, but it's missing the top boundary. Here's the circular one. You can see the surface. Here's a square one. You can see the surface just going across it. And then this is a completely different shaped channel altogether. So the fluid is just flowing down these and along it. They have a variety of different slopes, etc. So what we know is that the flow has a characteristic length and it has a characteristic velocity. That means that we can consider the ratio of the inertia forces, which is mass times acceleration, to gravitational forces. So those are the two forces that are in operation. So the ratio of inertia to gravitational force, okay, well, inertia force is basically mass times acceleration, and the gravitational forces is mass times gravity. So you can see we can cancel the mass just there. We're left with acceleration over gravity. Well, acceleration, we know from our mechanics, can be expressed as basically v dv dx, or v times v upon L. So if we rearrange this equation now, we get v squared over square root over g times a length, L. So this is where we take a number called the Froude number. And this is a very, very important number. Typically, this length scale, which I did not define here, is taken as the depth of flow in your channel. Okay, so the water depth. So the Froude number V is equal to V over the square root of G times H. So the square root of G times H is a velocity. Okay, so this is a non-dimensional number. It has no units. The square root of GH is a velocity, which we'll talk about in just a second. So this is the Froude number. This is a very important number, and you'll hear engineers talk about the Froude number all the time in the same way you hear about the Mach number and the Reynolds number. Okay? Right, so what values does that Froude number have? Well, let's consider this flow situation. We've got flow going from left to right over a bump in the channel. Okay, and we're going to look at our values of Froude number. So here, in this region, we have fairly slow-moving flow, okay, and this is called subcritical. And in this region, the Froude number is less than 1. So the fluid is very tranquil, okay, it's not moving very fast. But then suddenly the flow hits this bump, okay, and it speeds up because it has to maintain conservation of mass. And at this point, the Froude number will go to the value 1. And this is called the critical Froude number, or it's called critical flow, just in this region here. And then when the fluid goes over this bit of the bump just here, it's then accelerating. And so it's getting faster. And as it goes faster, you then have a very rapid flow, and the flow here is called supercritical. And here, the Froude number is greater than 1. So this is how we will be able to understand the types of flow that we have. So remember, the Froude number is the ratio of the inertial forces to the gravitational forces. So if the Froude number is less than 1 or the Froude number is greater than 1, we would expect very different behavior. And indeed, we do get this. Very, very different behavior in this region, subcritical, and this region, supercritical. Okay, so I just said the Froude number is the ratio of the inertia forces to the gravity forces. But there's another interpretation to this. So remember I told you that this square root of GH is actually a velocity. Okay, and we actually give it the symbol c. And if you look at what goes on the surface of the water, if you throw a stone into a pond or a puddle or something like this, you can see all of these nice rings, okay, just propagate out. The speed that those rings propagate with is given by this, because they're just moving with a characteristic speed. So these rings are propagating with the square root of g times h. So the Froude number can therefore be considered as the ratio of the flow velocity over the wave speed, so the speed of this surface here. You might begin to think, this sounds a little bit like the Mach number. So we're going to look at the equivalence of this Froude number and the Mach number. So when the Froude number is greater than 1, okay, we have that the velocity of the flow is greater than the characteristic speed of any disturbance. So that means the fluid is moving faster than any disturbance can propagate. So if you try to propagate a disturbance upstream against the flow, against velocity, you cannot, because the velocity is greater than the disturbance speed. So you cannot change the upstream conditions. On the other hand, if the Froude number is less than 1, that means that the velocity of the flow v is less than this characteristic speed, square root of gh. This means we can control what happens upstream, and we can control that with hydraulic structures. So this is analogous, this is very similar to the Mach number when we consider sound waves in a compressible fluid. So the Mach number, okay, is the flow velocity over the sound speed. And here we've got the flow velocity over the wave speed. So it's very, very similar. So when you're at supersonic flow, okay, that means your Mach number is greater than 1. So that means that you would arrive before the sound of your arrival. That's what supersonic means. Well, the equivalent is with supercritical flow for open channel flows. So the analogy between the Froude number and the Mach number is very close. It's quite an easy one to understand. What about the pressure distribution? The pressure distribution, I always say, is very important. Well, if the cross-section and the slope of this channel here is varying quite slowly, okay, and the pressure itself is varying slowly, so we don't have a violent flow, right, then we can say that the vertical acceleration is much, much less than gravity. And so we can then assume that the pressure is hydrostatic. So the pressure distribution inside an open channel flow is generally hydrostatic. So it's increasing linearly as we go further down. So this equation here says my pressure at any point is equal to rho g times the depth of water above. So z surface minus z, where z is measured upwards. So that's hydrostatic pressure. This is important because now we can return back to our concepts of total head or total pressure that we met with the Bernoulli equation earlier in the course. So, at any point in the flow, we define the total head to be the pressure over rho g plus z plus v squared over 2g. So this was our definition of total head, which is equivalent to total pressure and equivalent to total energy. Now, our definition of the piezometric head is the pressure over rho g plus z. We met this before, and this was the hydraulic grade line. We met this very, very briefly in one lecture. So this is called the piezometric head. If we substitute in our expression for pressure, this was our hydrostatic pressure. If we put that in here, and we just substitute the value in just here, you can see we've got a minus z here and a plus z here. Those two cancel because the rho g's here cancel, and we're just left with the height of the water above the bed, above our datum point, sorry, z surface is equal to the piezometric head. So that means that our total head, if we go and substitute in for our piezometric head, okay, is equal to z surface, so this, where's my mouse gone? Point up here, plus v squared over 2g. Now, by definition, the location of my surface, my fluid surface, must be equal to the height of the bed above my datum plus the depth of flow above it. So I can just substitute this into my total head expression, and I have that the total head is equal to the location of the bed plus the depth of water plus the dynamic head. So these are just definitions we're dealing with here, but they're ones in which engineers become very interested. In particular, the specific energy. So this represents the total energy head above the channel bed, or the channel bottom at any section. So this is H plus V squared upon 2G. So H here is the water depth. So you'll hear hydraulic engineers talk about the specific energy, or the specific head, or the specific pressure. And this is what they're referring to, because it's very useful. So, at any point in the flow, the total head, or the energy per unit weight, is equal to the location of the bed, plus the depth of water, plus the V squared upon 2G term. That's if there are no losses. But we know in reality there really are losses, because we've got bed friction. You've basically got friction on the wall, which in this case is the bed. Just here, we call this the bed. But you also sometimes get large energy losses. When you get violent flows, such as we saw in the first image, this is actually a form of energy dissipation by nature. And so it's losing energy. We're going to come to a very special one in a second called the hydraulic jump. Right, so it's piazza pole time. This is testing whether you've actually been awake during all of that. So here we've got flow going under a sluice gate. So here's the gate just here. And so here we've got subcritical flow on the left because it's very slow moving. And suddenly you get supercritical flow here because it's moving very fast as it comes under the gate. And then boom, we get a hydraulic jump and the flow slows down again. So this is subcritical. So the question here is, which of the following sets of Froude numbers are correct? Is it A, where you've got on the left the Froude number is less than 1. Here, in the supercritical region, Froude number is equal to 1. And then here, the Froude number is greater than 1 and subcritical. Or is it B, where you've got Froude number less than 1 in the subcritical region. In the supercritical region, Froude number is greater than 1. And then in the subcritical region, we have Froude number is less than 1. So, what is your answer? The poll should already be opened. Right, let's see how you guys voted. Okay, so here is the piazza poll. And look at this. 98% of you say B. You make me very happy this morning. Very good. Right, so what is the right answer? The right answer is B, so very well done, okay? For that one person who voted A, you need to look at the lecture notes again, okay? All right, so why is it B? Well, when the flow is subcritical, the Froude number is less than 1, and when the flow is supercritical, the flow is greater than 1. Should be fairly clear, I hope. All right, now we met something here, this hydraulic jump. Okay, what is this hydraulic jump? I just introduced it without telling you. Well, a hydraulic jump is an abrupt change from a shallow, high-speed flow to a deep, low-speed flow of lower energy. So you can hear this is a picture, I think it's from somewhere in China. And you can see the flow is coming out very, very fast. And then suddenly, for what might appear no reason whatsoever, it suddenly jumps up in its height. Just boom. It's flowing very, very fast and then suddenly jumps up. And there's nothing underneath that would make it do that. So this kind of thing happens when there is maybe a change in the slope or the water depth. And it does that in order to compensate for the high frictional losses in the flow. So you might have very high losses on the surface when the flow is going too fast, and so it jumps up, it jumps away from the friction boundary almost. Alternatively, you might have a difference in the height upstream and downstream, and this will create the conditions for a hydraulic jump, and we're about to see that now. So if I go here, right. So if I go, okay. So this is a hydraulic jump, and if we just look here, okay. So this is in a lab. You can see it's coming in very fast on the left here, and then boom, it just suddenly jumps up. So no, not that one. Okay, so we can do this in the lab here. It's very easy. You basically get a very, very fast-moving flow coming in here on the left, and then all of a sudden, it just jumps up, and you get all these bubbles. It's very violent, okay, and then suddenly the water is at a much greater height here. This is almost, I don't know, maybe 10, 20 times the height of the flow coming in here. So there's a lot of energy loss going on between these two cases. So across a hydraulic jump, the mass is conserved, the momentum is conserved as well. Okay, the momentum principle is satisfied, but losing mechanical energy. And actually, most of that energy is being converted into heat. And the type of jump you get here depends upon the conditions upstream and downstream generally. Now, in some cases, okay, that formation of a hydraulic jump can be a really good thing, because if you've got a huge amount of water coming down a spillway or coming down a pipe at high velocity, you want to reduce some of that energy, because otherwise it can do a lot of damage to anything downstream. So hydraulic jumps, they can be very, very useful things to be able to control and understand. So we're now going to analyze a hydraulic jump, literally exactly as you saw in the video just there, and we're going to make some assumptions. It's a horizontal channel. We've got a rectangular cross-section of uniform width W. The velocity we're going to assume is uniform over the cross-section. That's quite satisfactory. So the velocity across here is all V1, and the velocity across here is all V2. The boundary layer basically is incredibly thin to the point where we don't have to worry about it. There is negligible bed friction over the length of the jump. So going from here to here, okay, we're not going to worry about bed friction, because the energy losses that happen here in this frothing zone, okay, are much, much greater than the friction losses. So we're going to go through the basic steps of the analysis. We're going to apply continuity, so that's conservation of mass. Then we're going to apply conservation of momentum. And then we're going to investigate the energy loss. How do we actually get that energy loss? All right, so conservation of mass. What goes in must come out. First thing we do, though, is we draw a control volume. So there is our control volume drawn around the area of interest. So we've drawn the control volume around the hydraulic jump. And so here is point 1 at the inlet, and then here is point 2 at the outlet. So we've got depth h1, depth h2, velocity v1, velocity v2. It's a rectangular channel with a uniform width of W. So the flow of mass per unit width is constant, so we can say the mass flow rate in must equal the mass flow rate out between points 1 and 2. Well, when we express m dot, it's rho times the area times the velocity. So we've got rho A1 V1 is equal to rho A2 V2. The areas A1 and A2 are different because you've got different heights there. So A1 is equal to the width of the channel times the depth H1. A2 is equal to the width of the channel times the depth H2. We can cancel the rhos in that equation, the densities here, the rho, and we can substitute in our expressions for A1 and A2, and our continuity equation becomes a very simple H1 V1 is equal to H2 V2. We're going to use that information in a little bit because we have an expression for V1 and V2 there. All right, conservation of mass done. Now let's do conservation of momentum. So we've got our control volume over our hydraulic jump here. And what you've got at the inlet and at the outlet is you have a hydrostatic pressure distribution. So the pressure at the surface is effectively 0, and then the pressure at the bottom here is rho GH1. Here the pressure is rho GH2. So from that hydrostatic pressure distribution, we can get an average pressure that acts over each face. And that will give us a force. So the average pressures at 1 and 2 are given by a half rho GH. Okay, so this is the general expression for the average pressure here acting on this face and on this face here. And then we're going to apply the momentum principle. So the momentum principle, just to remind you, you would have done this with Professor Rebel, is the net rate of flow of momentum out of a control volume must equal the force on the fluid inside the control volume. Okay, the net rate of flow of momentum out of a control volume. So the net means whatever comes out minus whatever comes in. So that's what the net rate of flow is. So here are our equations. So the flow of momentum out is going to be equal to the mass flow rate times velocity. And we do the same at the inlet, except that this is now negative because we're looking at the net rate of flow out of a control volume. The force on the fluid inside the control volume, well, the only forces acting are the pressure distribution forces just here. So we've got the average pressure over face A1 and minus the average pressure over the face A2, because we're taking the positive x direction from left to right. We substitute in our expressions for m dot, so here we've got rho V2W times H2 times V2, and we do the same here. And then we've substituted in for our areas here. So this is WH1 is equal to A1, WH2 is equal to A2. So far, so good. We're just applying the momentum principle. Now we want to cancel things that we are on both sides of the equation, and we also want to introduce our average pressures. So the average pressure at point 1 is a half rho GH1. And the average pressure at point 2 is a half rho GH2. So we're just going to put those expressions into here. You can see that we can already cancel the W's. Okay, the W's there will just cancel. Nice and easy. And we substitute our expressions in for our average pressure. And now we've got this nice equation in terms of V2, H2, V1, and H1. The rhos, you can see, the densities are already going to cancel. So if we do a little bit of tidying up, we get V2 squared times H2 minus V1 squared times H1 is equal to half G H1 squared minus H2 squared. We now use continuity from the previous page to eliminate the velocity V2. So here's my velocity V2, but I'm going to substitute in from the expression I have from continuity, which is V1 H1 over H2. So all I've done is I've substituted in just here this expression. So I get V1 squared into H1 squared over H2 squared times H2. So it's quite a nice, simple expression. We're nearly there. We're nearly finished. Just to note that I could easily have calculated the force by integrating the local pressure distribution over the depth here. Okay? I could have decided not to use average pressures, but actually done this force integration just there. So we're going to simplify that expression that we just derived. h1 squared minus h2 squared, you can factorize this as h1 minus h2 into h1 plus h2. We do that so that we can cancel this h1 minus h2 term. This gives us a nice expression for v1 squared, okay? And you can begin to see that we can understand how to compute the Froude number. So we have a very similar expression for v2 squared, except that you'll see here that this ratio of h2 over h1 is flipped. And that's basically from using continuity. So our Froude numbers that we defined earlier, here is fr1 squared, which is equal to v1 squared over gh1. Here is fr2 squared, which is equal to v2 squared over gh2. Very, very similar, except that you've just got this h2 over h1 term here is flipped. So we've derived an expression for the Froude numbers just by looking at the momentum analysis. So we have expressions for velocity, and we can get expressions for the Froude number. So let's just think about this for a second. On the left, h1 is small. It's smaller than h2. Okay? So that means that h2 is bigger than h1, and h2 over h1 is greater than 1. So if we consider this equation here for Froude number, that means our Froude number is greater than 1. It's supercritical, which we knew already, but now we've proven it. If we look at Froude number for point 2, now h1 upon h2 is less than 1, and so this expression here now reduces to fr2 is less than 1. So therefore it's subcritical. So with our analysis we've been able to show that this is supercritical and this is subcritical on the right. So fairly straightforward once you just go through the motions. Now, the last thing was to look at the energy loss. So remember that the total head was equal to v squared upon 2g plus the water depth h. So the change in the total head, delta h, is equal to h2 minus h1. So it's just this expression for point 2 minus the same expression for point 1. We have expressions for v1 squared and v2 squared. So if I rewrite this equation now as v1 upon 2g into v2 squared minus v1 squared plus h2 minus h1, after a little bit of algebra and rearranging, I end up with this expression here of delta h is equal to h1 minus h2 all to the power cubed over 4h1. Question: is h1 bigger or smaller than h2? Smaller. All right, it's smaller. So is delta h here, this head loss, is it positive or negative? Negative. So with it being negative, that means we are losing energy. We're losing total head, okay? So the mechanical energy cannot increase in this transition zone when we go through this hydraulic jump region, okay? We have to lose energy. So this is an energy dissipation region. And that energy loss rises sharply with the difference in the water depth, okay, because this is to the power cubed. Okay, so let's do a worked example, see how this works out. Flow in a 150 millimeter wide horizontal channel jumps from a depth of 50 millimeters to 150 millimeters. So you've got 50 to 150 millimeters. What are the upstream and downstream velocities, the volumetric flow rate, and the rate of energy loss at the jump? Okay, so these are the questions that are being asked in this particular case. So first of all, we just try to interpret the question. There's a hydraulic jump in a horizontal channel. This means that we can use the equations that we just derived to compute the quantities requested in the question. So we're given the width, W, was 150 millimeters. The height, H1, was 50 millimeters. The height, H2, was 150 millimeters. Immediately, we can say, well, the ratio of H2 over H1 is 150 over 50, which is equal to 3. We've done this because we know that's in our equations. So for the upstream velocity, V1 squared, okay, this was our expression we derived, half g H2 over H1 into H1 plus H2. We just plug in all of our numbers, and V1 squared comes out as 2.943, and our velocity V1 is 1.72 meters per second.
I have a question about the assumption that we have taken in the analysis.
Okay.
Since there is mechanical energy loss, some of the water must evaporate, or not all of it, but some of it must evaporate. Then the assumption that mass is conserved, we can't take this assumption, right?
Okay, good question. But did you see the speed of the hydraulic jump video? It's fast. Okay, the water goes from supercritical to subcritical in fractions of a second. It is far too fast for evaporation to take place. There is some slight heating of the fluid, but we're not at boiling. We're nowhere near it. So it's possible there might be a tiny fraction of evaporation. And I mean tiny, I mean like 1,000,000 times less in terms of energy loss compared to the actual jump condition. So for the purposes of our analysis, for engineers, we don't care about something that's so small. Now, if your fluid was heated, okay, and it was actually near the boiling point and you were doing a hydraulic jump, then you might have to start considering it. But I mean, you're literally just below the boiling point, so that evaporation starts to become something that you should consider. It may turn out it's not important. But good question, and I like the way you're thinking, so thank you very much. Okay, let's carry on with the worked example. The downstream velocity, V2, is exactly the same. We just put in all of our values and we get an answer of 0.57 meters per second. So we have all of these quantities because these are just water depths. Alternatively, we could have done that more quickly just by using continuity, and it would have given us exactly the same answer, so 0.57 meters per second. The question asked us for the volumetric flow rate. Well, Q, that's the volumetric flow rate, is equal to the area times the velocity. We have all of these terms. We have the width, we have the water depth, and we have the velocity. So we substitute in all of our values just here, and that will give us 12.9 liters per second. Yeah. This flow rate is in meters cubed per second. Yeah, which I've converted to liters per second. Okay. Good, you're all awake. I like it. It's great. Finally, the question asks for the rate of energy loss. Now, in the analysis, all we worked out was the total head change, if you remember. Delta H. We can work that out. Here's delta H. Here's our expression for delta H, which is, and you get this cube term on the top. We can work out that. And the change in the total head is basically the difference between v squared over 2g plus the water depth between points 1 and 2. But to work out the rate of energy loss, we have to remember the equations we used in the steady flow energy equation. So the rate of energy loss needs a mass flow rate. So m dot times gravity times the head loss. And the head loss in this case is going to be equal to delta H. So our mass flow rate is rho times area times velocity, which is equal to rho times the flow rate Q, and the head loss is equal to delta H. So our expression for the rate of energy loss is equal to rho times G times the flow rate times delta H. So I'm now going to I'll just go back. We're now going to work out each of these quantities, or I'm just going to work out delta H because I've already got rho, G, and Q. And I put in my values, and there's delta H minus 0.0333. It's negative, as we discussed before. And so the rate of energy loss, when I put in all of those values into my equation for the energy loss rate, rho times G times Q times delta H, is minus 4.22 watts. So these are all useful engineering quantities. Yes, another question?
I had a doubt regarding the definition of open channel flow.
Okay.
An open channel flow can be defined as flow that is covered on three sides and having only one place.
In effect, yes.
So does that mean that if I pour water out of a bottle, can that flow be considered as an open channel?
So the question is, if you pour water from one glass to another, is that an... Yeah, so, and then as the water travels, is that open channel flow? Is it in a channel? No. So it's not open channel flow. It's still a free surface. It still has the free surface, but it's not an open channel flow. Okay, so my end of lecture task, rather than a question for this time, it's a task for you. Today we have examined the key concepts of open channel flow. All right? Now, your task, if you choose to accept it, is to find a hydraulic jump in your accommodation. All right? That is your task. There's a hint to find a hydraulic jump in your accommodation. So that's open channel flow, the Froude number, the total and specific energies for open channel flow, and the hydraulic jump. Remember to have a go at the questions for Thursday. Thank you to those who've been wearing a mask. See you then. See you on Thursday.